So, when we think about how humans learn, we usually picture that classic image of a student cramming for a final exam.
Oh, yeah, totally. The 2 a.m. coffee-fueled panic.
Right, you're sitting there at 2 in the morning just desperately trying to memorize every single word from like a whole semester's worth of lectures.
And you just assume that remembering absolutely everything is the only way you'll pass.
Exactly. But I mean, what actually happens? You sit down for the test and your brain just completely freezes under the weight of all those isolated facts.
Because you focus so much on memorizing every little bullet point that you completely miss the actual big picture of the course.
Yes. And it's funny because it turns out the most advanced artificial intelligence models in the world do something incredibly similar.
It really is a common cognitive trap, even for machines.
So welcome to today's deep dive. Today we're looking at how we make artificial intelligence cheaper, faster, and surprisingly enough, much smarter by teaching it how to let things go.
Which sounds completely backwards at first.
Right. But we are pulling back the curtain on a really foundational state-of-the-art paper from researchers at RBC Borealis. The paper is titled Coverage-Driven KV Cache Eviction for Efficient and Improved Inference of LLM.
It's definitely a mouthful of a title, I'll admit that.
Just a bit. But the implications behind it are massive for the future of AI, right?
Oh, absolutely. I mean, as generative AI models scale up and become more integrated into our daily lives, they're hitting a very real, very rigid physical wall.
Which is what we're going to get into.
Yeah, because we spend so much time focusing purely on how smart an AI is, evaluating its logic and reasoning capabilities, but solving the hardware and memory constraints is just as critical.
Because if we can't physically run these models efficiently on everyday hardware, their raw intelligence doesn't really matter.
Exactly. It's just a Ferrari with no gas in the tank.
I love that. So that's our mission for this deep dive. We're going to explore this hidden memory bottleneck that makes AI so incredibly expensive and, computationally heavy to run.
And the fix is honestly brilliant.
It is. We'll unpack this new method that actually teaches the AI how to forget the right things so it can preserve the context that actually matters.
Taking a literal peek under the hood of models like Llama 3.
Yeah, the mechanics of it are just fascinating. So to really appreciate how this new method fixes the AI, we probably first need to understand why the AI is breaking under the weight of its own memory in the first place.
Right, which brings us to the core engine of an AI's short-term memory, which is the KV cache.
Okay, let's unpack the KV cache because it sounds like a highly technical term, but it's really just the AI's workspace, right?
Pretty much, yeah.
So what's going on in there that makes it such a monster for computer hardware?
Well, KV stands for key value. So when a large language model, or LLM, reads a really long piece of text.
Like, say you feed it a massive 500-page PDF document about corporate law.
Exactly. It processes that text token by token, or basically word by word.
Okay, makes sense.
Now, when it's time for the AI to generate a summary or answer a question about that law document, it really doesn't want to reread that entire 500-page PDF from scratch for every single new word it generates.
I mean, that would take an agonizing amount of time.
Right. So the model stores its intermediate calculations, its attention states,
Yeah.
in a temporary memory bank.
And that memory bank is the KV cache.
You got it. It's saving its work as it goes, essentially holding on to the context of everything it just read.
Okay, so going back to our cramming student analogy, the KV cache is essentially the notebook the student is using during a semester-long lecture.
That is a great way to visualize it.
They're jotting down notes so they don't have to reread the massive textbook every time the professor calls on them to answer a question.
Exactly. But here is the structural problem with that notebook. In the architecture of modern LLMs, specifically how the self-attention mechanism works, the AI has to figure out how every single word relates to every single word that came before it.
Oh, wow. Every single word.
Every single one.
Hmm.
Because of that, the size of the notebook grows quadratically as the input gets longer.
Wait, quadratically. Let's clarify that math for a second because I think people often mix up exponential and quadratic.
They do, all the time.
We aren't just saying it grows fast. We're talking about a very specific mathematical curve here.
Yes, and the distinction is really crucial. It's not exponential growth, where a number doubles itself over and over like a virus spreading.
Right.
It's quadratic growth, which is based on the square of the input.
Yeah.
So think of it this way. If a document is 100 words long, the model isn't just doing 100 calculations.
What is it doing?
It's comparing word 100 to the 99 words before it. then word 99 to the 98 words before it.
Oh, I see. It's mapping an entire grid of relationships.
Exactly. So if you double the document length from 100 to 200 words, the memory required doesn't just double, it quadruples.
Yikes.
And if you increase the length by 10 times, the memory requirement goes up by 100 times.
So by the end of a long document, the student isn't just carrying a thick notebook. They're hauling around a notebook the size of a minivan.
And that minivan is parked directly inside the computer's RAM.
Which is a
A
problem.
huge problem. The K-VEC cache becomes a massive memory overhead. Its size scales with both the sequence length of the input and the depth of the model's neural layers.
So in real-time or resource-constrained settings, this just completely limits scalability.
Completely. The memory footprint becomes so large that the graphics cards physically run out of space and the system just crashes or grinds to a complete halt.
Which explains why you, the listener, can't just download a massive state-of-the-art AI and run it natively on your smartphone right now.
Right, the hardware just isn't there.
It's also why API costs for developers go through the roof when they start feeding entire books or code bases into these models. The sheer hardware required to hold that giant, quadratically growing notebook is wildly expensive.
And the engineering community is very aware of this bottleneck.
I
Since we can't just buy infinite RAM to hold an infinitely growing notebook, engineers have tried to force the AI to throw away its old notes.
Okay, and this process is known as cache eviction.
Exactly, cache eviction.
So if the notebook is full, the strategy is basically just telling the AI, you're out of paper, start ripping out the useless pages to make room.
That's the idea.
But how does the AI currently decide what's useless?
Well, the current standard relies on something called attention sparsity.
Attention sparsity, okay?
Yeah, methods out there right now with names like SnapKV, Streaming LLM, and Pyramid, they all operate on the same basic assumption.
Which is?
That an AI doesn't actually need to pay attention to every single word to understand a sentence.
Sure, humans do that too. We skim.
Right. So these methods look at the AI's internal attention scores, keep only the most important tokens that score the highest, and just dump the rest into the garbage.
Okay, that sounds logical on the surface, but if the AI is smart enough to read a dense legal contract and answer complex questions about it, shouldn't its own attention scores already know perfectly well which tokens to keep?
You would think so.
So why does throwing away the low-scoring tokens cause the AI to suddenly fail at its job?
It's a completely fair question. And it's the exact mystery the researchers at RBC Borealis wanted to solve.
And what did they find?
When they dug into the eviction scores used by methods like SnapKV across the model's various layers and attention heads, they uncovered a pretty fatal flaw in the model's psychology.
Oh.
Yeah. The AI is actually terrible at deciding what to throw away because it suffers from extreme recency bias.
Recency bias, meaning it overly values whatever it just read a few seconds ago simply because it's fresh.
Exactly.
Mm.
And the researchers provided some brilliant visual evidence of this in their paper, specifically in Figure 3.
What did they do?
They gave the AI a multiple-choice reading comprehension test. In this specific test, the text was quite long, but the actual correct answer to the question was presented right at the very beginning of the prompt.
Oh, tricky.
Yeah, and when they visualized what the existing eviction methods were doing, the results were just glaring.
Let me guess. The existing methods completely ignored the beginning of the prompt.
Completely. They assigned almost zero attention to the correct answer.
Wow.
Instead, they clustered all their high attention scores heavily on the final few tokens of the text.
So the AI literally threw away the correct answer just because it appeared on page 1 instead of page 10.
Yep.
That feels entirely counterintuitive for a machine we consider intelligent.
It's actively sabotaging itself. It throws away the critical information because of this severe skew toward the end of the input sequence.
It gets tunnel vision.
Exactly. Tunnel vision.
Oh.
But what makes this so destructive is that this pattern repeats across all the different attention heads and layers of the model.
So they're all making the same mistake.
Yes. You have all these different computational pathways that are supposed to be looking for different things, but they're all independently looking at the exact same recent tokens and deciding, hey, these are the most important.
Oh, man. So every single layer saves the same few words at the very end and discards everything else.
Exactly.
It's like having a team of 32 brilliant detectives assigned to investigate a massive crime scene in a mansion.
I like this.
Right. But instead of fanning out to check the bedrooms, the basement, and the study, all 32 detectives crowd around the exact same muddy footprint at the front door.
That is exactly what happens.
They're all staring at it, completely ignoring the murder weapons sitting in plain sight on the kitchen counter.
The visual of the detectives is spot on. The model layers are all duplicating each other's work while completely losing the broader context of the house.
Which is terrible for solving the crime. Or the prompt.
Exactly.
Yeah.
Now, observing this recency bias in an experiment is one thing, but what elevates this paper to foundational status is that the researchers didn't just point out the problem.
Right, they proved it.
They actually proved mathematically why this tunnel vision breaks the AI's predictive brain.
And this is where they brought in information bottleneck theory, right?
Yes, they did.
Which sounds like a very heavy academic concept. Can we get, and explain it, I'm 5 on what that theory actually is?
Absolutely.
Hmm.
Think of information bottleneck theory, like trying to pack for a year-long trip across different climates, but you're only allowed to bring one single tiny suitcase.
Okay, highly stressful.
Very. You clearly can't bring everything you own. The theory basically states that the ideal compression, the perfect way to pack, gets rid of all the redundant items, but keeps the exact unique items you need to survive.
So no packing 5 identical black t-shirts.
Exactly. It squeezes out the noise, but perfectly preserves the essential predictive signal.
Got it.
In AI terms, you are squeezing a massive input through a tiny computational bottleneck, and you want the output to still be highly accurate.
So the researchers applied the suitcase packing theory to the AI's memory cache.
They did. And through that, they proposed the coverage hypothesis.
Okay, what's that?
Well, in this specific context, coverage simply means the total number of unique tokens that are retained in the K-VEC cache at least once across all the different heads and layers.
Unique tokens. So taking it back to our detectives, coverage is a measure of how many different clues they are looking at in total across the entire mansion, rather than a measure of how intensely they are staring at one single footprint.
You've nailed the dynamic. The researchers mapped this out mathematically. Let's say your input prompt is X, and the answer you want the AI to generate is Y.
Right.
The K-VEC cache is the bridge between them. They proved an irreducible mathematical trade-off.
Which is?
If token coverage drops, meaning your detectives are all looking at the same few words and your unique token count is low, the mutual information between the input and the output plummets.
Mutual information, meaning the meaningful connection between the question I asked and the answer the AI gives back.
Right. The capacity of the cache to hold diverse, non-redundant information fundamentally limits its prediction performance.
That makes total sense.
If the coverage is low, the mutual information shrinks, and the AI's ability to answer accurately just collapses.
Because it doesn't have the pieces.
Exactly. You absolutely need diverse tokens to maintain context over a long document. You can't just keep the most highly attended tokens if they're all clustered in the exact same paragraph at the end of the text.
You need a wide spread of unique information.
Yes.
Okay, so we've diagnosed the disease. The AI is failing at long context tasks because its memory eviction strategies lack unique coverage.
Right.
The layers get tunnel vision, they all save the same stuff, and the mutual information drops. So what's the cure? How do we force the AI to look at the whole picture?
That brings us to the core innovation designed by the RBC Borealis team, which they call K-VEC.
K-VEC.
It stands for K-VEC Cache Eviction with Coverage.
Love a good acronym.
Always. It's a novel strategy built from the ground up to prioritize token coverage while the AI is deciding what to throw away.
Awesome.
And it attacks the problem from 2 distinct angles.
Let's break down this two-pronged attack. If they're trying to fix the tunnel vision, I imagine the first step is dealing with the individual attention heads themselves.
That's exactly where they start. The first prong is called crosshead coverage.
Okay.
In a transformer model like Llama 3, you have multiple attention heads operating in parallel within a layer.
Right.
Normally, they all compute their eviction scores entirely independently, and they usually only look at a tiny observation window, often just the most recent 16 tokens.
So they're extremely short-sighted.
Very. K-VEC alters this by seeking out the heads that are unfocused.
Wait, how does the system mathematically define an unfocused attention head? How does it know?
Good question. It actually calculates the standard deviation of their attention scores.
Okay, taking me back to statistics class.
I know. But if a head has a very low standard deviation, it means its scores are nearly uniform across all the tokens it looks at.
So it's not spiking on any particular word.
Right. It's not differentiating well. It's basically just looking at a blur.
Gotcha.
So K-VEC strategically targets these specific unfocused heads and forces them to widen their view. It expands their observation window from 16 tokens to 32 tokens.
Ah, I see. So if a detective is just staring blankly at the floorboards, not really seeing anything useful, KVE taps him on the shoulder and says, "Hey, stop looking at your shoes, widen your gaze, and look at this entire half of the room."
That's a perfect way to put it.
It forces the lost heads to capture a much broader set of tokens, which naturally pushes the overall coverage up.
And it does this without distracting the heads that are highly focused.
Nice.
But that's only the first half of the solution. The second prong is cross-layer coverage. And this is where the system introduces real coordination.
Okay, how so?
K-VEC actively tracks how many layers have already saved a specific token.
So instead of operating in complete isolation, the layers are actually communicating with each other now.
Yes, they share information through what K-VEC calls a coverage score.
Okay, walk me through that.
Imagine layer 1 is processing the text and decides to save a specific word, let's say the word plaintiff, in a legal doc because it seems important.
Okay.
K-VEC logs that action. Now, when the data passes to layer 2, and it's layer 2's turn to decide what to save, KDEC assigns the word plaintiff a high coverage score.
Interesting.
Layer 2 sees that high score, applies a penalty to that token, and actively biases its own search toward a different, less tended token.
Oh, wow. So if layer 1 already bagged the muddy footprint as evidence, layer 2 is essentially told, we already have high-resolution photos of the footprint, go find something else.
Exactly.
It systematically forces the deeper layers to diversify their memory.
It creates a beautiful balance between global importance and novelty. The system computes a focus score that ensures layer 2 doesn't just pick a random meaningless word, but rather picks a highly relevant word that just hasn't been heavily saved by previous layers yet.
Okay, I understand the logic, but I have a genuine question about how this plays out.
Sure.
If we are actively forcing the AI to look for new tokens just for the sake of diversity, just to push that coverage number higher, isn't there a huge risk of accidentally saving a bunch of useless junk?
Oh, you mean like filler words?
Yeah. Won't the later layers start filling their precious limited memory budget with commas and periods and the word "the" simply because no other layer wanted them?
It's a great point, and the researchers anticipated that exact vulnerability.
Oh, they did.
Yeah, you can't just maximize coverage blindly, or you dilute the memory with noise and lose the critical signal entirely.
Right.
To prevent that, K-VEC is built with a strict, non-negotiable failsafe.
Okay, how does the failsafe operate?
It utilizes a layer-wise retention ratio. K-VEC takes the total memory budget for a layer and sections off its strict 25%.
25%.
Right. That 25% is reserved exclusively for the absolute highest priority tokens based purely on their raw, original attention scores.
Oh, I see.
For this top tier, K-VEC completely overrides the coverage penalty. It guarantees that the most critical, highly attended information is kept, regardless of how many other layers saved it.
So it's protecting the VIP tokens.
Exactly.
Yeah.
It essentially says the top 25% of our budget is for the obvious, undeniable clues. We aren't risking those.
Right.
The remaining 75% of the budget is what we'll use to enforce diversity and map out the rest of the context.
That's incredibly elegant. It guarantees you don't accidentally throw away the murder weapon just because you were busy looking for new clues, but it still forces the team to investigate the entire house.
And it's the synthesis of these mechanics. The expanded window for unfocused heads, the anti-redundancy penalty across layers, and the 25% fail-safe budget that makes K-VEC such a robust architecture.
Okay, so the math is sound, and the architecture makes a ton of sense on paper. But theoretical elegance doesn't always translate to performance.
Very true.
Let's talk about the proof in the pudding. How did K-VEC actually perform when exposed to real-world, messy, long context data?
Well, the researchers put K-VEC through a grueling gauntlet. They implemented it on a Llama 3.18b instruct model, and they evaluated it across 16 different subsets of the Longbench dataset.
And Longbench is pretty much exactly what it sounds like, right?
Yeah, for context, Longbench tests everything from single document question answering to complex multi-document reasoning, long-form summarization, and even parsing massive blocks of synthetic code.
Basically a decathlon for the AI.
Exactly.
And looking at the data here, the numbers are phenomenal. Let's highlight the Casper dataset, which focuses on highly context-sensitive question answering.
Right, like asking an AI to extract a very specific finding from a 30-page academic research paper.
Yes, and the researchers heavily constrained the AI's memory budget, limiting it to just 128 tokens.
Which is practically nothing.
Right. At that tiny budget, the existing eviction methods basically collapsed. But KVC outperformed them by a massive 10.35 points.
A 10.35-point leap in the context of these specific benchmarks is seismic.
It's huge.
It really demonstrates that when an AI is severely starved for memory, KVEC's ability to retain a diverse set of KV pairs is literally the difference between the AI hallucinating a failure and successfully retrieving the correct answer.
The results for the famous needle in a haystack test are even more striking.
Oh, I love this test.
For those who might not be familiar, this is a test where researchers hide a single, random, highly specific fact deep inside a giant wall of unrelated text.
Literally hiding a needle in a haystack.
Exactly. And then they ask the AI to find it. It requires the AI to maintain perfect context across a massive document while ignoring a sea of noise.
It's considered the ultimate stress test for long context retrieval.
So how did it do?
Well, in this test, the leading existing method, SnapKV, managed a score of 87.4.
Okay, not terrible.
Not terrible, but KVEC, on the other hand, jumped all the way to 98.2.
98.2. It essentially perfected one of the hardest retrieval tests we have.
And we can trace that success directly back to the information bottleneck theory we discussed earlier.
How so?
When they measured the overall token coverage during that test, the existing method was sitting at just 86.6% coverage. KVEC pushed that unique token coverage up to 94.5%.
Oh, wow.
By systematically forcing the attention heads and layers to look at a wider variety of unique tokens, KVEC ensured that the single crucial needle wasn't accidentally thrown in the trash during the cache eviction process.
It's so satisfying when the theoretical math perfectly predicts the real-world benchmark.
It really is.
But there's a pragmatic angle we have to address, and I know developers listening are probably thinking about this right now.
The cost.
Yes, if we are forcing the AI to coordinate all these layers, track what layer 1 is doing, compute standard deviations for every attention head, and apply coverage penalties, doesn't all that extra computational math slow the AI down? What is the actual cost of running KVEC?
The computational complexity trade-off is usually the catch with these breakthroughs.
Right.
But what makes KVEC so viable for deployment is how minimal the overhead actually is. First, in terms of memory overhead, KVC uses the exact same memory footprint as existing methods.
So that's not taking up more RAM.
No. It stores the same number of tokens, it's just much smarter about which tokens it chooses to store. So there's zero memory penalty.
That covers memory, but what about speed? Let's break down the actual processing time, because LLMs operate in two distinct phases, right?
Yes.
You have the prefill stage and the decoding stage.
Right. Let's separate those because it explains the cost perfectly. Phase 1 is the prefill stage.
Which happens when?
This happens the moment you hit enter. The AI takes your entire 500-page PDF, digests it all at once, and builds that initial KV cache.
Okay.
Phase 2 is the decoding stage. This is when the AI actually starts spitting out the answer, generating text one single word at a time.
Right. So where does KVEC add to the workload?
KVEC operates almost entirely during that initial prefill stage.
Ah, okay.
Because it has to calculate the standard deviations and coordinate the coverage scores across the layers, there is a very slight delay during prefill.
Like how slight?
It takes a tiny fraction of a second longer to read the prompt and organize its notes.
That's it.
Yeah. However, during the decoding stage, when the AI is actually generating the answer, KVEC's speed is completely identical to existing methods like SnapKV. There is zero delay in token generation.
So it takes a tiny bit longer to prep, but writes just as fast.
Exactly. And here's why that matters for real-world application. For modern LLM tasks that involve long-form reasoning, the output sequences, the answers the AI generates, are typically very long.
Sure, paragraphs and paragraphs.
As the AI generates hundreds or thousands of tokens in its response, that tiny one-time initial delay from the prefill stage gets completely washed out.
It just disappears into the total time.
Mathematically, it becomes negligible. The overall time complexity ends up being practically identical to existing approaches. You are getting a massive boost in accuracy and context retention, essentially for free.
Wow, that's a developer's dream. So, to summarize the journey we've taken today, why is this deep dive into KVEC such a massive win for you, the listener?
It's all about scalability.
Exactly. We are rapidly moving into a world where we expect AI to process our entire code bases, analyze years of financial records, and summarize entire books in seconds. But until now, the AI's notebook just got too massive.
And when we told the AI to start throwing notes away to save memory, it suffered from recency bias and just threw away the beginning of the book.
Right. What the researchers at RBC Borealis have achieved is figuring out how to optimally evict those tokens without losing the broader narrative.
By bridging the information bottleneck theory with practical cache eviction, they proved that maintaining diverse token coverage is the secret to preserving mutual information.
They built a system that actively fights tunnel vision by enforcing cross-head and cross-layer coverage.
And in doing so, they are paving the way for incredibly smart, long-context AIs to run smoothly, accurately, and efficiently on hardware with highly constrained memory limits.
It fundamentally changes how we think about the architecture of memory in these models, which leaves me with a final, somewhat philosophical thread for you to pull on as we wrap up today.
Oh, I'm curious.
Well, in human psychology, we often equate intelligence with the raw ability to retain information, right? We idolize the concept of the photographic memory, the person who remembers every face, every date, every tiny detail.
The ultimate trivia champion.
Right. But when we look closely at how KVEC improves the reasoning capabilities of an artificial brain, we uncover a slightly different truth. The true hallmark of an efficient, high-performing mind, whether it's a biological student trying to pass a final exam or a billions of parameters artificial intelligence processing a legal document, might not actually be the ability to remember everything.
That makes a lot of sense.
True intelligence might actually be the absolute mastery of knowing exactly what to forget.
It's a profound shift in perspective. Prioritizing the meaningful, diverse context over the endless, redundant details.
That's the key. Thank you for joining us on this deep dive into the mechanics of memory. Keep exploring, keep questioning, and we'll see you next time.